Chemical kinetics and catalysis. In this unit, we will study catalysis, general characteristic of catalyzed reaction, homogeneous and heterogeneous catalyst, inhibitors, poisons and promoters, significance of catalyst. Catalysis. There are many substances which increases the speed of reactions without being used up in the reaction. For example, during the preparation of oxygen, when potassium chlorate is heated strongly at 653 to 873 Kelvin, it decomposes very slowly. However, when a little amount of manganese dioxide is added, the decomposition occurs considerably at lower temperature range of 473 to 633 Kelvin and also at much faster rate. It is interesting to note that the added manganese dioxide remains unchanged with respect to its mass and composition. Potassium chlorate, when heated in the presence of manganese dioxide, which act as a catalyst, oxygen gas is produced. So here we see that when catalyst is not added, we have to heat potassium chlorate strongly at 653 to 873 Kelvin, and this process is very slowly. And when we add manganese dioxide, which act as a catalyst, the temperature is lowered 473 to 633 Kelvin and reaction take place at much faster rate. And the catalyst we have used, manganese dioxide, it remains unchanged. There is no change in the mass and composition. Definition: a substance which alters the rate of chemical reaction without itself undergoing any change in mass and chemical composition at the end of the reaction is called a catalyst. The phenomenon of increasing the rate of reaction by the use of catalyst is called catalysis. We can also define catalyst. It is a substance that increases the rate of reaction without itself being consumed in the reaction. Positive and negative catalysis. If a catalyst increase the rate of a chemical reaction, it is called a positive catalyst and the phenomenon is called positive catalysis. If a catalyst decrease retards the speed of a reaction, it is called a negative catalyst. And the phenomenon is called negative catalysis. For example, oxidation of sulfur dioxide to sulfur trioxide in the presence of vanadium pentaoxide, which act as a catalyst in the contact process, is an example of positive catalysis. So generally here vanadium pentaoxide increases the rate of chemical reaction. However, the decomposition of hydrogen peroxide H2O2 in the presence of acetanilide or phosphoric acid gets retarded and is an example of negative catalysis. So there are two types, positive and negative catalysis. Catalyst which increases the rate of chemical reaction, it is called positive catalyst. And when a catalyst decreases the rate of chemical reaction or the speed of a reaction, then it is called negative catalyst. Catalytic reactions. There is a comparison of activation and energies of a catalyzed and a, an uncatalyzed reaction. So this is a graph between energy and a reaction progresses with the reactant is converted into a product. When catalyst is added, it is shown by a red line, and in the absence of catalyst, it is shown by blue line. Uncatalyzed reaction, and red lines show catalyzed reaction. So here we see activation energy. So activation energy is the minimum energy that is required for a reacting molecule to get converted into a product. So in this graph, we see a transition state and a transition state in which where uh, old bonds are broken and new bonds are formed. It is the intermediate state. So here we see that when a catalyst is added, it provides an entirely a new path for the reaction in which the reactants are converted to product quickly, which is shown by red line. A chemical reaction take place by reaction path first converted to activated state or transition state, and then finally to the product. A catalyst form a new activated complex of lower potential energy. This means that catalysts provide a new pathway of lower activation energy. Consequently, the fraction of the total number of collisions possessing lower activation energy increased, and hence the rate of reaction increases. So in this graph we see that the activation energy in the presence of catalyst EA1 is less than activation energy in the absence of catalyst EA2. Catalysts generally increase, yes, speed up the rate of chemical reaction, and the reaction take place at much faster rate in comparison to uncatalyzed reaction. It takes times as it is shown in the graph between energy and reaction progresses with time. General characteristic of catalyzed reaction. Next step, general characteristic of catalyzed reaction. The catalyst remains unchanged chemically at the end of the reaction. This means that the amount of substance uh, the amount of the catalyst recovered at the end of the reaction is found to be same as the amount of catalyst taken at the beginning of the reaction. This means that the catalyst remains unchanged. There is no increase or decrease in the mass and composition of the catalyst. Next point, only a small quantity of catalyst is needed for carrying out the reaction. A very small amount of catalyst is required to convert very large amount of reactant into the product. Next, a catalyst does not affect the state of equilibrium in a reversible reaction. This means that a catalyst accelerate both the forward and the backward reaction and helps to attain the equilibrium quickly. At equilibrium, the rate of forward reaction is equal to rate of backward reaction. A catalyst has no role, it only helps to attain the state of equilibrium quickly. Next, a catalyst does not initiate a reaction. It simply increases or decreases the speed of reaction. The main function of the catalyst is to provide alternative path for the reaction which requires lower activation energy, which we have seen in the previous graph, uh, comparison of activation energies of catalyzed and uncatalyzed reaction. Next, a catalyst is specific in its action. In the first example, we have seen in the preparation of oxygen by heating potassium chlorate, we have used manganese dioxide as a catalyst. But the use of manganese dioxide as a catalyst for other reactions, generally it fails. For different reactions, different catalysts are used. For example, for hydrogenation of fats, in which nickel is used as a catalyst. In Haber's process, nickel iron is used as a catalyst. In the oxidation of sulfur dioxide to sulfur trioxide, vanadium pentoxide is used as a catalyst. So a catalyst has a specific in its action. Next, a catalyst has an optimum temperature. Uh, this means that a catalyst can act effectively at a particular temperature for a specified reaction. This temperature is known as optimum temperature. For example, the optimum temperature for oxidation of sulfur dioxide to sulfur trioxide in the presence of platinum catalyst is 450 degrees Celsius to 500 degrees Celsius. Therefore, a catalyst has an optimum temperature, not more than 450, yeah, not less than 450 or more than 500 degrees. It is between 450 to 500 degrees Celsius in case of oxidation of sulfur dioxide to sulfur trioxide. So these are the general characteristic of catalyzed reaction. Classification of catalyst may be of two main types: homogeneous catalyst and heterogeneous catalyst. Homogeneous catalyst. When the catalyst is present in the same phase means solid, liquid, or gas, as the reactants and product. It is called homogeneous catalyst. If the reactant and products are in the gaseous phase, then the catalyst should also be in the gaseous phase. Then it is called homogeneous catalyst. For example, in lead chamber process, sulfur dioxide is oxidized to sulfur trioxide in the presence of nitric oxide as catalyst. So sulfur dioxide when react with oxygen in the presence of nitric oxide, it gives sulfur trioxide. So here we see that all the reactant, product, catalyst are in the same phase, that is gas. Second example, catalytic decomposition of ozone in the presence of nitric oxide or chlorine atoms as catalyst in the gas phase. So ozone plus oxygen atom in the presence of nitric oxide or chlorine atom which are in the gaseous phase give oxygen. So here we see that all the reactants and product are in the same phase. Next example, hydrolysis of an ester is catalyzed in the presence of an acid. Ethyl acetate uh, when react with water in the presence of mineral acid like concentrated sulfuric acid, it gives ethanoic acid or acetic acid plus ethyl alcohol, which are all in the same phase, that is aqueous state. So these are the example of homogeneous catalyst. So here we see that the catalyst which is present in the same phase as the reactant and products are present. Next, heterogeneous catalyst. When the catalyst is in the different phase than the reactants and the product, it is called heterogeneous catalyst. For example, manufacture of ammonia from nitrogen and hydrogen by Haber's process using finely divided iron as catalyst. When nitrogen react with hydrogen in the presence of iron as a catalyst, which is in the solid state, give ammonia. So reactant and products are in the same phase, gaseous state, but catalyst is in the different phase, that is solid state. Next example is dehydrogenation of ethanol by using nickel catalyst. Dehydrogenation means removal of hydrogen. So when ethyl alcohol, ethanol, is heated in the presence of nickel as a catalyst which is in the solid state, so ethanol acetaldehyde is formed plus hydrogen gases evolve. So here we see that here we see that catalyst nickel which is present in the solid state is different from reactant and product. Next example is oxidation of ammonia into nitric oxide in the presence of platinum gauze in Oswald process. Ammonia react with oxygen in the presence of platinum, which act as a catalyst, is in the solid state, give nitric oxide and water. So reactant and product are in the same phase, but the catalyst is in different phase. So these are the examples of heterogeneous catalyst. The catalyst may be divided into mainly two types: homogeneous and heterogeneous catalyst. Homogeneous catalysts are in the same phase as the reactant and the product. In case of heterogeneous catalyst, the catalyst are is in the different phase than the reactants. Inhibitors, poisons, and inhibitors are substances which slow down the rate of reaction by interfering in the action of catalyst. Inhibitors are the substance which generally slow down the rate of reaction by interfering in the action of catalyst. The main role of catalyst is to increase the rate of reaction, but inhibitors slow down by interfering in the action of catalyst. For example, in enzymatic catalysis, if any substrate structurally similar to the substrate or product, then it may bind to the enzyme and slow down the reaction. Poisons. Poisons are the substance which decrease the activity of the catalyst. The role of the poison is to decrease the activity of the catalyst. For example, certain substances like carbon monoxide, arsenic, etc., if present, act as poisons because they lower the activity of the catalyst. Promoters. Promoters are substances that enhance the activity of the catalyst. We can say that the promoter are the substance which uh, increases the efficiency of the catalyst. For examples, in Haber's process for manufacture of ammonia, molybdenum is used as promoter for iron, which act as a catalyst. Nitrogen when react with hydrogen, it give ammonia. So here iron act as a catalyst and molybdenum act as a promoter. The main role of promoter is to increase the efficiency of the catalyst. So here what we see, inhibitors generally slow down the rate of reaction by interfering in the action of catalyst. Poisons are the substance which decrease the activity of the catalyst, and promoters are the substance that enhance, yeah, increase the efficiency of the catalyst or enhance the activity of the catalyst. Significance of catalyst. The main significance of catalyst is in the production of fine chemicals, food processing, and processing of fuels. Production of fine chemicals. Catalysis is used to make a variety of fine chemicals. Methods include heavy industry operations as well as more specialized procedures that would be extremely costly on a big scale. The Heek reaction is an example in which an unsaturated halide is treated with alkene in the presence of base and palladium catalyst to form a substituted alkene. Because most bioactive molecules are chiral, enantioselective catalysis or catalytic asymmetric synthesis is used to make many medications. The first significance is the production of fine chemicals. Food processing. The hydrogenation, interaction with hydrogen gas. The hydrogenation of fats with nickel catalyst to generate margarine is one of the most visible application of catalyst. We have seen when hydrogenation of unsaturated hydrocarbons. Unsaturated hydrocarbons means double bond and triple bond is treated with hydrogen in the presence of nickel, platinum as a catalyst, then saturated hydrocarbon is formed. Biocatalysis is also used to make a variety of other foods. So this is the significance of catalyst in food processing. Next, processing of fuels. Alkylation, catalytic cracking, which breaks long chain hydrocarbons into smaller pieces. Naphtha reforming and steam reforming are all used extensively in petroleum refining. Conversion of hydrocarbons into synthesis gas. So, catalysis is used to treat even the emissions from fossil fuel combustion. Catalytic converters, which are usually made of platinum and rhodium, are used to break down some of the automotive exhaust most dangerous components. So these are the significance of catalyst: production of fine chemicals, food processing, and processing of fuels. So in this unit, we have seen about the definition of catalyst. The catalyst are the substances which are used to increase the rate of reactions without itself consumed, and types of catalyst. There are mainly two types: homogeneous and heterogeneous catalyst. And then the definition of inhibitors, poisons, and promoters, and significance of catalyst.